morning, ladies and gentlemen. My name is Michal Šprlák and I come from the University of West Bohemia in Pilsen. Together with my department colleagues, we have worked on the classical geodetic subject titled Far Zone Effects for Integral Transformations. Let me start with an introduction. You certainly know the apparatus of integral transformations. These mutually connect various quantities of the gravity field. The existing mathematical links are depicted by the Meissel diagram on the slide, with the disturbing potential T on the left up to its third-order spatial derivatives on the right. We summarized this rich class of spherical integral formulas in our article that got published in Earth Science Reviews in 2017. Consider now the Poisson integral in the box. In theory, we integrate the products of the boundary values T with the kernel H over the entire spherical surface. However, the gravity data may not be available over the whole sphere, either due to distribution policies or impracticality of their collection. In practice, therefore, we decompose the global integral into two parts. The first, black part, within the spherical cup, is the effect of the near zone. The second, blue part beyond the spherical cup, is the far zone effect. Accurate quantification of the far zone effect has been examined for some simple integrals. We have continued in this quest for all mathematical links illustrated on the previous slide. And in this talk, I would like to share some experience on the related theoretical and numerical aspects. Let us focus firstly on mathematics and consider the far zone effect for the Poisson integral. The goal is to transform the restricted integral at the top into its spectral representation at the bottom. The harmonic series at the bottom can be easily calculated from a global gravity field model and a set of Fourier coefficients Qn acting as spectral weights. The transition from the integral into the series is straightforward, and it includes the 5 steps listed on the slide. You can robotically apply this 5-step procedure and obtain harmonic series for all isotropic boundary values, such as the radial potential derivatives of an arbitrary order. Complications come with anisotropic and non-homogeneous cases. One such example is the analytical solution of the horizontal boundary value problem. The boundary values are the horizontal derivatives of the potential T. Notice that the kernels k phi and k lambda are also functions of the backward azimuth alpha prime. When converting the far zone effect in the box into its spectral equivalent, you may end up at the step 1 of the 5-step procedure and eventually conclude that further progress is impossible. Fortunately, I could find a technical way to overcome this issue and called it step 0. Namely, I rewrote the kernels k phi and k lambda such that they were always expanded into orthogonal series. Overall, we derived spectral forms of the far zone effects up to the third order potential derivatives. All formulas were generalized for arbitrary radial derivative of any boundary value. Complete mathematical proofs take up around 250 pages that demonstrates the great extent of the theoretical work. Closed-loop simulation validated the extensive theory by comparing integral and spectral forms of the far zone effects. We employed the most recent global gravity field model from the Tongji collection. From this model, we calculated global grids of the potential and of its radial derivatives at the mean sphere with the angular resolution of 0.05 degrees. The evaluation was performed at 450 computational points from the realistic orbit of the GOES satellite. Their position is indicated by the red dots in the figure. All quantities were synthesized between the harmonic degrees 2 and 250. From 80 integral formulas tested, I chose here only 2 sample results. The first one is for the Poisson integral. The far zone effect for the 5-degree spherical cup is illustrated by the blue line. It reaches several tens of meters squared per second squared along the track. The red line shows the differences between the 2 representations of the far zone effect. These are 3 orders of magnitude smaller than the signal and cannot be distinguished from the 0 value. The second sample result is for the 3rd order radial derivative of the Poisson integral. The far zone effect has a wider range and a higher variability along the track. The differences are close to 0 and expected and are at least 2 orders of magnitude smaller than the signal. Thus, we have a numerical proof that the derived formulas for the far zone effects are truly correct. Let us look at some properties of the Fourier coefficients. We examine these to understand their connection with the kernels or to eventually detect potential numerical issues. I selected first example for the Poisson integral, band limited between the harmonic degrees 0 and 20 for the computational point at the GOES orbit. The kernel is depicted at the top as a function of the spherical distance on the horizontal axis. It reaches maximum at psi equals 0, and with the increasing spherical distance, it oscillates around the 0 value. The 2-dimensional plot below depicts the corresponding Fourier coefficients. These are functions of the spherical cup size psi 0 on the horizontal axis and of the harmonic degree on the vertical axis. The amplitudes of the Fourier coefficients are systematically positive in a close proximity of the kernel's maximum. Then their numerical values change sign and their magnitude gradually reduces. Interestingly, the amplitudes of the Fourier coefficients reach local extrema at the 0 crossings of the kernel. For curiosity, I also examined the case of the 3rd order radial derivative of the Poisson integral. The kernel again has its maximum at psi equals 0, and then it oscillates around the 0 value. The corresponding Fourier coefficients keep more or less a similar pattern to the previous slide. In contrast, the numerical values of the kernel and of the Fourier coefficients are significantly larger for the 3rd derivative of the Poisson integral. These strong fluctuations indicate that the calculation of the far zone effect in this case may be prone to potential numerical issues. I stop exactly here and go to the conclusions. In this talk, we took the challenge of completing the Meissel diagram for the far zone effects. We derived in total more than 80 spherical harmonic series for all gravity field quantities from the disturbing potential up to its third order derivatives. All formulas were extensively validated in closed-loop simulations. We also systematically examined selected mathematical properties of these series, for example, by looking at the behavior of their Fourier coefficients. We are now completing a few research papers, and we hope that you will read the full story very soon. In addition, we are developing a software library written in MATLAB for calculation of the far zone effects, and this software will be freely available to all potential users. In the end, I would like to advertise two posters by my colleagues Martin Pitoniak and Petr Trnka. These are extensions of our work on the far zone effects and will be displayed during the poster session today in the afternoon. That is all from my side, and I would like to thank you for your attention.